knows a lot about the science stuff. Professor Dave explains.
Quantum chromodynamics, or QCD, is the quantum field theory that describes the strong nuclear force. It explains the behavior and interactions of quarks through a mediator boson known as a gluon. First, let's talk about how quarks make up hadrons, which can be produced from QED interactions between electrons and other particles. Then we'll dive into an overview of the quark model. Remember how there is an electric charge within QED that is affected by the theory and is an important part of interactions? Similarly, there is a color charge within QCD that is affected by the theory and is an important part of QCD interactions that we'll discuss next. We'll touch on how gauge symmetries were used to develop QCD from a quark model into a full quantum field theory, talk about Feynman's rules for QCD, and wrap up with learning about how the scientific community was convinced by this new theory through the discovery of a new particle. There is an interesting bridge from QED to QCD. When an electron and a positron collide, there is a chance that they will produce a quark and an antiquark. As the quarks fly apart from the interaction, they start to produce other quark-antiquark pairs, and then these pairs join together to form particles like mesons and baryons. These are both types of hadrons, which are just groups of quarks, which is why the process is called hadronization. These particles are emitted in two distinct jets, which point back to the original tracks of the first quark and antiquark. This has been experimentally measured, with the data lining up pretty well with the theory. However, there is a slight difference. We're thinking of this process as a QED interaction of electrons to quarks, leading into a QCD interaction of quarks combining to form hadrons. This isn't completely accurate. The quarks can actually be thought of as virtual particles in bound states that represent the hadrons. Since we know that quarks make up hadrons and are the important interactions within QCD, let's talk a little bit more about quarks specifically. Quarks were originally proposed by Murray Gell-Mann and George Zweig in the 1960s to help address the growing problem of the particle zoo that was being slowly discovered. Scientists kept finding more and more new particles with all different masses and properties, and many believed that the chances of all these particles being fundamental decreased as more were discovered. The quark model offered a solution, proposing that there were three quarks that combined in different ways to create hadrons. These were the up quark, down quark, and strange quark. Later, the model was further developed to include the fact that quarks combine with gluons in complex ways to form hadrons. This is the current theory behind the internal structure of hadrons and is being tested in experiments around the world. There are two main groups of hadrons within the quark model. Baryons are made up of three quarks. For example, the proton and neutron are up-up-down and up-down-down, respectively. Since we know that the proton has a positive electric charge and the neutron is neutral, this implies that the charge of the up quark must be positive 2/3 e, and the charge of the down quark must be negative 1/3 e. Here, e is the fundamental charge, 1.6 times 10 to the negative 19 joules. The other main group of hadrons is called mesons, which are made of one quark and one antiquark. All of the quantum numbers of a baryon or meson are made of the quark quantum numbers. As a result, quarks must have isospin and hypercharge and other quantities of that nature. The numbers are added together to get the overall quantity corresponding to the hadron, as we just saw in the case of the electric charge of protons and neutrons. Speaking of numeric particle descriptors, there is a signature quantum number of QCD that is so important that it appears in the name of the theory. That is color, hence the term chromodynamics. In 1973, Harold Fritsch, Heinrich Leutwiler, and Murray Gell-Mann formalized the idea of color charge as the fundamental source of the strong nuclear force. It was first proposed to solve an issue within the existing model of hadrons. There were some particles that appeared to have three quarks in the same exact state. Due to the fact that quarks are fermions, Pauli's exclusion principle tells us that this isn't possible. The only way that these quarks could all exist in that state is if they have another different property, corresponding to another quantum number. From this, color was born. The three possible colors within QCD are red, blue, and green. While color in this context has nothing to do with visual colors, these three were chosen as an analog because when quarks of all three colors are combined, the total color is neutral, similar to the way that red plus blue plus green is white. The visual color analogy does fall apart a little bit with the idea that anti-quarks have colors of anti-red, anti-blue, and anti-green. Color should be thought of within QCD as electric charge is thought of within QED. However, there is one interesting distinction between electric charge and color charge. In QED, photons are neutral and are therefore mediators of electromagnetic interactions but do not carry electric charge themselves. This means that photons don't interact with each other in QED. As a result, as you get closer to an electromagnetic system, or in the language of particle physics, go to higher energy scales, the effective charge increases due to fewer electron-positron pairs getting in the way. This is known as screening, defined as when the coupling constant of an interaction increases with energy. In QCD, gluons are the mediators of the strong interaction, but they themselves have a non-neutral color charge. This results in self-interaction between gluons, which creates an anti-screening effect. When you go to higher energy scales, the coupling constant decreases and the effective color charge decreases. Eventually, at high enough energies, the coupling constant essentially vanishes and the particles in QCD become free particles. This is known as asymptotic freedom, and its existence as a part of the strong nuclear force is a key difference from the theory of electromagnetism. The idea of asymptotic freedom leads to another interesting property of the strong nuclear force that arises from QCD. At very high energies, quarks can essentially free stream as independent particles. This would be seen at early universe energy scales. What happens at very low energies, or the energy scales that are present in our universe today? It would seem that quarks cannot exist freely due to the increasing strength of the coupling constant as energy decreases. This is a phenomenon known as quark confinement. As the energy decreases, or equivalently as the distance between quarks increases, the strong force becomes so powerful that it prevents quarks from separating and becoming free particles. If one quark attempts to separate, the energy required is so large due to the strength of the quark coupling that a quark-anti-quark pair would be created between the separating quark and the others. This would then form new groups of bound quarks, and instead of a free-streaming quark, there would be new hadrons. This is why, at the low energies of our current universe, quarks are always bound together inside particles like protons and neutrons, and have never been observed in isolation. The color confinement hypothesis states that the only particles which are free, and therefore observable, are always color neutral. Since observable matter is made of color neutral combinations of quarks, protons and neutrons must contain one quark of each color to maintain this color neutrality. To put all this theory into more mathematical language, let's discuss the symmetry that is required within QCD. It's a type of gauge symmetry known as SU3. Without getting too deep into the linear algebra, SU3 is a slightly different version of a gauge symmetry than the one present in QED, which was U1. SU3 corresponds to a conservation of transformations that are a rotation within color space, which looks like a multiplication by e to the I times vector theta alpha, which contains multiple angles, times a gell-mann matrix lambda alpha divided by 2 by convention. These gell-mann matrices are called the generators of the SU3 group. One thing to note is that just as Maxwell's equations arise from the U1 gauge group for electromagnetism, there is an analogous set of equations for the SU3 gauge group. In fact, Maxwell's equations are the special U1 case of the more general Yang-Mills equations, which describe the dynamics of gauge fields for many possible symmetry groups. In the SU3 case, Yang-Mills theory can be seen as a generalized version of Maxwell's equations in which the force carriers, gluons, interact with each other. Interestingly, one of the Clay Millennium Prize problems, a set of some of the most pressing unsolved questions in mathematics, is related to these equations. Gluons gluons seem to be massless, but bound states of gluons have been found to be massive. This indicates that there is a mass gap that appears somewhere in the math of QCD, but no one has been able to find where. If someone was able to rigorously prove that there is a proper Yang-Mills theory that contains a mass gap, they would win $1 million, as well as lots of fame and notoriety across math and science. Let's now take advantage of Feynman diagrams to make more sense of this math. We can define the vector C as the color, and we have three versions of this vector which correspond to the three colors. These colors usually change at quark-gluon vertices in Feynman diagrams, since gluons can carry color charge. The Feynman rules for QCD are very similar to QED, except with a few new ones to account for the new particles. 1. External lines add in the following factors, assuming the particle has momentum p, spin s, and color c. Incoming quark, u of s and of p times c. Outgoing quark, u adjoint of s and of p times c dagger, where the dagger is the complex conjugate and transpose of c. Incoming antiquark, nu adjoint of s and of p times c dagger. Outgoing antiquark, nu of s and of p times c. Incoming gluon, epsilon mu of p times A alpha, where by convention gluon color is defined as A rather than C. Outgoing gluon, complex conjugate of epsilon mu of p times the complex conjugate of A alpha. We should again note that U and V are the particle and antiparticle spinors as defined from the Dirac equation, and the bar on U or V means the adjoint of that spinor. 2. For every internal line, add a factor for quarks and a different factor for gluons. 3. For each vertex, whether quark-gluon, 3-gluon, or 4-gluon, add a different factor. All of this math is useful, but scientists require experimental proof before they accept things to be true. What was the evidence that was able to convince scientists that QCD was an accurate and descriptive theory that should be incorporated into the standard model? The pivotal moment was known as the November Revolution of 1974. That November, a new particle was discovered simultaneously by Sam Ting at Brookhaven National Laboratory and Burton Richter and Martin Pearl at Stanford's SLAC National Accelerator Laboratory. Ting's team called it the J particle, and Richter's team called it the psi. Thus, the particle was known as the J-psi particle. It's a meson made of a charm and anti-charm pair. The observation of this particle was the first detection of a quark other than the original three, the up, down, and strange. Previously, the particle had been predicted by some theorists. Since it was created using a proton beam shot at a target in Brookhaven and electron-positron interactions at SLAC, the theorists who used QCD to predict the particle's existence were validated by this new particle discovery. Additionally, the idea of quark confinement held up even in the presence of this new quark. This meant that the previously accepted three-quark model was wrong and kicked off years of frantic searching for further quarks around the physics community. Scientists at Fermilab subsequently found the bottom quark in 1977 and top quark in 1995. Thusly, the 6-quark sector of the standard model was filled in. As we've seen, QCD is a mathematically complex theory that proposes a simple yet profound truth. Quarks are never found alone. They're permanently confined within color-neutral particles. Additionally, QCD offers the ability to extend the calculations of QED to more Feynman diagrams and more particles. However, unlike QED, where the coupling constant is small enough to allow easy calculations via quantum mechanical perturbation theory, QCD becomes too strong at low energies for this approach to work. This has led to the development of lattice QCD, a numerical technique that discretizes spacetime and uses powerful supercomputers to simulate quark and gluon interactions. These calculations have helped scientists make more predictions about particles that were later found to be correct, further confirming the validity of QCD. The theory is also valuable for understanding the early universe, especially when temperatures and energies were high enough for quarks and gluons to exist freely. At this time, the universe was made up of something called the quark-gluon plasma. There are currently experiments running around the world at both the LHC and Brookhaven National Laboratory that study this unique phase of matter, and we'll talk more about these experiments later in the series. QCD does a phenomenal job of understanding the strong force, but is also a perfect example of the deep unity between mathematics, theory and experiment in modern physics. In this sense, QCD is another display of how the Standard Model is a triumph of the scientific method. Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.